Okay, so get this. You're driving, right? And you pull up your phone, punch in your destination, and boom, like magic, a route appears.
It's like having a little navigator in your pocket. But did you know that digital map, that route it just charted, is all thanks to coordinate geometry?
And that, my friend, is exactly where we're diving deep today into your source material 7, coordinategeometry.pdf.
We're talking about the fascinating intersection of algebra and geometry.
Where those two worlds collide.
And this document, it takes something as abstract as points on a graph and shows how they translate to real-world problem solving.
And by the time we're through this deep dive, you'll grasp not only the distance formula, but also the section formula.
And trust me, these aren't just some dusty formulas in a textbook.
Yeah, we're talking about the formulas that underpin everything from, well, like we said, navigation apps.
To understanding the very shape of a triangle.
Speaking of which, the source kicks off with this relatable scenario. Imagine trying to find the distance between two towns, one 36 kilometers east and 15 kilometers north of the other.
And they even give you a visual aid with figure 7.1.
Always helpful.
It's a clever way to introduce using the Pythagorean theorem to crack this distance puzzle.
Because at its core, that's what the distance formula is, right? A streamlined Pythagorean theorem for finding the distance between any 2 points on a plane.
Exactly, no matter how far apart those towns or points might be.
But we're not just talking maps here. Give me an example of how this pops up in a place you wouldn't expect.
Okay, how about facial recognition software? It uses the distance formula.
No way.
Yeah, to analyze the relative positions of key features on your face.
You mean like
Eyes, nose, mouth. It's creating a unique geometric signature for each person.
So it's like coordinate geometry is the secret sauce behind recognizing your best friend in a crowded room.
You got it.
Wow, I never thought about it like that. Okay, back to the document. It then throws this term at us, collinear points. Sounds kind of intimidating, but it's actually pretty straightforward.
Yeah, it's simpler than it sounds. Picture a straight line. Any straight line. Collinear points are just points that happen to lie on that same line.
Living their best life on that line.
Exactly. And this whole idea of collinearity will be crucial when we dive into calculating the area of triangles.
Love how it's all connected. All right, let's get our hands dirty with some real-deal examples from the source, because for me, that's when it really clicks.
Let's do it.
Example 1 throws down the gauntlet. Are these points, 3, 2, 9, 8, 2, 3, and 2, 3 buddies, forming a triangle? And if so, what kind of triangle are they building?
I love it. This is where the distance formula struts its stuff. We use it to calculate the length of each potential side of our triangle.
And don't forget that crucial triangle rule. The sum of any 2 sides of a triangle has to be greater than the third side.
Always.
So, spoiler alert, this trio of points actually does form a triangle, but it's not just any triangle, is it?
You're right, it's a special triangle. And we know that because if we look closely at the relationship between the squares and the side lengths, we see our old friend, the Pythagorean theorem, popping up again.
A blast from the past.
Right. And that tells us we've got ourselves a right triangle.
Just chilling there in our coordinate plane. Okay, what about example 3 with the classroom seating arrangement? I love that they give us figure 7.6.
Visuals are always a win.
We've got these 3 students, Ashima, Parthi, and Camilla, each sitting at specific coordinates. The question is, are they all in a line? Or are they forming, a more interesting shape?
Suspenseful.
So let me guess, the distance formula comes to the rescue again.
You bet. By calculating the distances between each pair of students, we can see if the sum of any 2 distances equals the third. If it does, bam, we've got ourselves a straight line of studious individuals.
And if not, time to rearrange those desks for better collaboration, maybe? But here's where I thought things got really neat. The document subtly drops this connection between the area of a triangle and those collinear points we talked about. It's tucked away in example 13.
It's like a little hidden gem. They explain that if you use the area of a triangle formula, which, don't worry, we'll unpack later, and you get 0 as your answer, it's a dead giveaway, that your points aren't actually making a triangle at all. They're chilling on the same line, being all collinear.
Okay, so we've tackled the distance formula.
We've figured out how to tell us points are collinear, but
Right, but what if?
what if we want to find the exact coordinates of a point?
Like a point that's dividing a line segment.
Yeah, but dividing it in a very specific ratio.
Ooh, okay, I see where you're going.
That's when the section formula swoops in to save the day.
It's like it's got our back.
Think of it this way. You've got a line segment, any line segment,
Okay, got it.
and you need to find that sweet spot.
That one precise point.
Yes. The point that divides the line segment, let's say, in a ratio of 2.1. The section formula. That's your secret weapon.
It's like having a mathematical GPS for pinpointing locations.
You got it. But this time, it's on a line segment.
On a line segment, on a map.
Exactly.
Okay, can we see this formula in action? What does it actually look like?
Of course. Here it is. For a point that's dividing a line segment with endpoints, x, y, and x, y, in the ratio MEO, the formula is, brace yourself,
I'm ready.
MEQ plus MEO, x plus MEO. See, I told you, a mouthful.
That's a mouthful. I'm still processing that.
It's a bit intimidating at first glance, but believe me,
There's a pattern there.
there's an elegance to it.
Okay, break it down for me.
Essentially, you're calculating a weighted average
Weighted average. Okay.
of both the x-coordinates and the y-coordinates, with the weights being those ratios, euro and euro.
Right, so it's like you're giving one endpoint a little more importance than the other.
Exactly. Depending on the ratio.
Okay, that makes a lot more sense now, but can we see it in action, like in a real-world situation? Because that's when these things really click for me.
Of course, and the source material has got us covered.
It always does.
Remember that example with the relay tower? Figure 7.9, it's all there.
Oh, yeah, that was a good one.
So we've got these two towns, right? And a telephone company needs to place a relay tower.
Makes sense. Got to boost that signal.
Right. But there's a catch. They want to position it so its distance from one town is twice its distance from the other.
So we're talking a 1.2 ratio.
You got it. And guess what?
The section formula saves the day.
Exactly. They use this scenario to show how the section formula helps find those perfect coordinates for the relay tower.
So it's all about optimization
Optimization of what?
of the reach, maximizing signal strength.
There you go.
It's like coordinate geometry is low-key the unsung hero of telecommunications.
That's everywhere.
Okay, so we've covered distances, collinearity, the section formula.
What's next?
How about something near and dear to my heart? The area of a triangle.
Ah, classic.
But using coordinates, that always felt like pure magic to me.
It is a pretty neat formula.
It is. It's like you're conjuring up the area out of thin air.
Well, not exactly thin air. We've got our trusty coordinates.
Right. But still, it's magical.
So for a triangle with vertices, x, euro, and x, the area can be found using this formula. 12 x euro plus x years.
Okay, seeing it written out definitely helps, but I think I need to see it in action to really wrap my head around it.
Of course, we're all about learning by doing.
Example time.
Example time. The source was kind enough to provide a step-by-step breakdown in example 11, showing how to use this formula to calculate the area of a specific triangle.
Perfect. I'm ready to see this formula work its magic because so far,
We've been on a roll.
unlocking the secrets of coordinate geometry one formula at a time.
It's incredible, isn't it, how these seemingly abstract concepts,
They have such tangible, real-world uses.
exactly, from telecommunications to technology, even everyday problem solving.
It's like we've been handed this powerful set of tools, like a decoder ring.
A decoder ring.
I like that. To decipher the hidden geometry of the world around us.
The world and beyond. But for now,
Right. We should probably move on to our concluding segment.
we've covered a lot of ground.
We'll recap all those key takeaways from our coordinate geometry adventure and leave you with a final thought-provoking question to ponder.
And we're back. We've been on quite a journey through the world of coordinate geometry.
We've tackled the distance formula, we've befriended those collinear points, and we've even mastered the art of the section formula.
We've come a long way.
We have. And you know what? You're now equipped with a powerful toolkit
It's true.
for not just understanding, but actually wielding the power of coordinate geometry.
We're not just learning about it, we're
Yeah.
using it. Exactly. You can now calculate distances between points, pinpoint the location of a point dividing a line segment in a specific ratio, and even reveal the area of a triangle, all using just their coordinates.
It's like we've unlocked a secret code
A secret code for what?
for deciphering the hidden geometry of, well, everything. Maps, technology, even the arrangement of objects in space.
It's all connected.
It really is, but here's something I've been pondering.
What's that?
We've explored all these concepts in 2 dimensions on a flat plane, but we live in a 3D world.
Ah, you're taking it to the next level.
What happens to these principles when we step into that extra dimension?
That's a fantastic question. And it highlights the beauty of coordinate geometry.
How so?
Because just as we use XY coordinates to define points on a flat plane, we can introduce a third coordinate, Z, to represent depth.
Whoa, mind blown. So it's like we're adding another layer to our coordinate grid.
Exactly. Taking it from a flat map to a dynamic model of our 3D world.
Okay, I'm following you, but do all those formulas we learned, like the distance formula and the section formula, do they still apply in this 3D world?
Absolutely. They have 3D counterparts.
No way.
While the calculations might involve an extra dimension, the fundamental principles remain the same.
So it's like the same rules, just a slightly bigger playground.
Exactly. It's a testament to the elegance and extensibility of coordinate geometry.
I love that. So all those insights we've gained, they're not limited to a flat plane.
Nope, they're stepping stones.
Stepping stones to understanding even more complex spatial relationships in our 3D world and beyond.
You got it.
What an incredible journey this deep dive has been.
It really has.
For anyone listening, don't be afraid to take these formulas for a spin.
Yeah, put them to the test.
Your source material even has practice exercises, so you can really test your skills.
Practice makes perfect.
It really does. And remember that aha moment we had connecting the area of a triangle to collinear points.
How can I forget?
That's just the tip of the iceberg.
There's so much more to explore.
There's a whole universe of fascinating connections and applications waiting to be discovered in the world of coordinate geometry.
So keep those minds engaged.
And never stop asking questions.
Curiosity is key.
Well said. Thanks for joining us on this deep dive into coordinate geometry.
It's been a pleasure.
Until next time, keep exploring, keep those aha moments coming, and most importantly,
Keep those minds hungry for knowledge.
couldn't have said it better myself.